Right. Good afternoon, everybody. Happy Election Day.
They're out voting.
It's a holiday of some type. Yeah, I hope those who are not here are out voting. That would be good. We should really have a nationwide holiday every election day. That'd be kind of nice. But alas, we're not quite there yet. I will say, if you haven't voted, go. Like, I'll even let you leave right now. Like, if this is the only time you could vote, go.
Okay.
I just want everybody voting, all right? Also, if you're not even registered to vote, you can still register today and vote. So go do that if you haven't. By the way, you know you could all like control the country, your age group, because typically voter turnout among 18 to 29-year-olds is really low. And if all of you like voted, you can make the country whatever you want it to be. And I would be completely disenfranchised and you'd be in control, and maybe that'd be good. You people are better anyway. Yeah, let the young people rule. So, let's see, what else? We've got an exam coming up a week from Thursday. The current plan, we've been talking a lot about current. So the current plan is to finish up this chapter today. I don't know exactly how long it will take, so we might start chapter 29 today, and I'm planning on chapter 29 being the last that's covered on the exam. If you're worried about like, a whole other chapter, I have to learn all of this stuff, 29 is kind of light. It's sort of like a setup chapter for the next one, which is a little more heavy. So it's not as big a deal as the one that we're doing right now. So it'd be kind of nice if we could sort of squeeze it in just to get some extra multiple choice questions and get us prepared for the last block of material. So that means that, first of all, you already had a homework assignment posted due Thursday. If you didn't see my email yet, I've moved that since we're just now finishing the chapter today. So that homework 28 is now due next Tuesday, which, keep in mind, there's going to be a homework 29 quickly following, and we have the exam next week, so try to stay on top of all that. The homework 29 will not be due before the exam. I'll make it due a few days after, okay? Also, I'm sleepy. Wow. I would like to know which one of you drugged me, because for like the last 2 hours, I've been sitting over in the office trying to get work done, and the whole time it's just been like this. Like I just can't focus, can't stop yawning, just complete and utter sleepiness that will not go away. So if I seem a little extra sleepy today, just yell at me every now and then and try to wake me up, scare me, do something, because I can't seem to snap out of it. And after this, I have to drive home in traffic for an hour. I'm going to die if you all don't wake me up somehow. You know how it feels like there's like literally like a weight sitting on your eyelids? Like, yeah, that is happening. I'm gonna blame it on the time change, just because that screws with everything.
An hour of sleep.
Huh?
You gained an hour.
I know, but it throws everything off. Like, I woke up at like 4:30 this morning feeling like it's time to get up. No, it's not. Go back to sleep. And that's happened the last 2 days, so everything's just all screwy.
I wake up at 6, thinking at 7.
Yeah.
And then I get my hour of sleep. So
See, that's pretty good, but waking up when it's all dark and terrible, and then you're like, yeah, it's no good. So alas, today is nap time. Let's just okay. Either vote or let's take a nap. So let's see where we were here. We were talking about Kirchhoff's rules. Let me just review, because at the end of class today, I'm going to give you all a problem for this to work, because I think it's a little confusing. Takes a little practice, so I'm going to give you guys one. It is one of your homework problems as well, so that should make you happy. But before we finish up this topic, let me just run through the rules once again. Now that you've actually seen one of these worked, perhaps they make a little bit more sense. When dealing with Kirchhoff's rules, you're essentially going to start by choosing a direction of current in every single branch of the circuit. Every branch has a different current, and you're just going to give it a name and pick a direction. Doesn't matter what you name it, doesn't matter which direction you choose, because the math will fix it for you at the end if it needs to. Also, you're going to use the junction rule to say for every two junctions you get one equation, and you're just going to say that what goes into that junction has to come out the other side. So that'll give you an equation that looks probably pretty similar to this most of the time. Then you're going to go around multiple loops of the circuit, kind of analyzing it or sort of like walking around different closed loops, doing different things in the equation for resistors and for voltage sources. When you're dealing with voltage sources, if the way you're analyzing takes you from the negative side of the battery to the positive, you can consider that a positive, an increase in voltage. If you're analyzing it the opposite direction, it's like you're stepping downhill, you'll put in a negative voltage. When it comes to resistors, it depends on whether you're going with the current that you've set up or against the current. If you're flowing downstream and you're going with the current, then voltage goes down as you go across a resistor. That's negative IR. If you're analyzing the circuit upstream, well, then you're sort of going uphill. Then as you cross a resistor, you put in a positive IR, or an increase in voltage. At the end of it, you're going to end up with a set of equations, a linear set of equations that you have to solve simultaneously using whatever method you want to use, and you're going to get some unknowns solved at the end of the day, all right? So we went through an example of that, working through the steps I just described. There that was. That is a colorful mess at this point, almost like the circuit's sort of hidden in there and you can't even tell it's there, all right? I'm going to give you one that looks, just so you know in advance, like this one, if maybe you've worked on that homework problem. It's, I think, easier than the one that we did in class, so maybe you'll be able to knock that out at the end of class pretty quickly. But what we're going to do is wrap up by talking about a few of these multiple choice questions with regards to Kirchhoff's rules. And then there's one other type of circuit that we're going to learn about in this chapter, and then follow up with something that might help you out in the lab going forward if perhaps you've already done stuff related to it. Maybe it'll retroactively help you understand things you did in lab already. But we'll talk about something related to lab. So first of all, there's a little piece of a circuit here. Notice it says there's 8 amps in the middle and 5 amps come in from here. They want to know how much must be going out branch P. Don't think too long. What goes in has to come out. The 8 is going to split back into 2 amps down, which leaves 6 amps to go to the right. Okay? So the 8 splits into 2. So you could probably tell me how much is in this branch over here as well, right? If it's 8 there, 5 here, what has to be here? 3. Okay? What goes in has to come out of each node. There are 2 nodes in this little piece of a circuit. Okay? This one, I'm going to let you read it and think about it for a second. All of you are going to get the answer wrong, but it's the thought process that's instructive a little bit, and then we'll talk through it. Okay? I'm just going to sit over here and take a nap. Just 30 seconds. That's all I ask. What are you thinking? Fantastic if you do that. And just wake back up feeling great. Any thoughts? Any answer you like that you'd like to tell me why you think that's the correct answer? What's that? I heard something. I like that. An answer, but you don't have to. I don't blame you, since I said most of you would get it wrong. It's okay. Yeah.
It gets brighter if it gets dimmer.
Because why?
Because A gets a second path, another path to lower resistance, while B gets a loses a path.
Okay. So you're going with, you said brighter?
Yeah, 4.
Number 4. A gets brighter, B gets dimmer. Okay. What else we got? It's not not necessarily easy. I see some other votes, some other people are in agreement. I see some other votes for 4. Going 5. Talk to somebody around you. Question? What's that? Answer?
Both bulbs decrease.
Both bulbs decrease.
So you're increasing the amount of path that you take to split up the current into several, which would then reduce the amount of or it would increase the resistance in order to have this.
Okay. So let's see, you said both of them decrease or increase? Decrease. So we've got, I've heard answers for all of those 3. You don't really like both bulbs going out, apparently. That doesn't seem likely. Okay, I would agree with that. Let's just go ahead and get rid of both bulbs going out. Intensity of both increasing, that also kind of seems unlikely. Let me remind you of something. Current flow. So, let's talk it through. We've got a variety of answers. See if any of you are kind of thinking the right path and maybe not saying it. 2 things I want to mention. First of all, I sort of analyzed the circuit a little bit as it stands, looking at the voltage increases and the voltage decreases. Remember, according to Kirchhoff's loop rule, when you go all the way around the circuit, the total changes in potential have to add to be 0 because I'm back in the same place. I can't like end up at a different height when I'm in the same location. So you could think of this as being positive 12 volts and another positive 12 volts. And then the only way that I'm going to get back to 0 over here, is if A and B are identical, is to have this one use up 12 and that one to drop another 12. That gets me back to 0, okay? So if I were to look at the potential at different points on the circuit, starting with here, just making an assumption that it's 0, because I could really pick any number, then this point in between is going to be at plus 12 volts. This point up here would be at plus 24. And then once I get over to this side of that resistor, we're back down to plus 12. And then when I get back to here, we're at 0. So what is the potential here? And what is the potential here? I just told you if you happen to remember. 12, right? That's 12, and that's 12. So if I close this switch, is number 2 satisfied? Is there any reason for any current to flow down that wire, even if I close the switch? No. Which means that it basically sits exactly the same as it did before. Ooh, it's like combining several ideas. So let me step through that one more time. So if we just look at the potential at different points in the circuit, again, you could say that we have just analyzing it clockwise. You could analyze it other ways if you want to. We can say that this is a step up in 12, which brings this to 12 volts, another step up of 12, which brings that to 24. This goes down 12, which brings this point back to 12, and then down 12 more gets me to 0, according to Kirchhoff's loop rule. If I'm going to have current flow, I need a path. Currently, when this switch is open, there's no path. So rule number 1 is not satisfied. But then when I close it, both ends of the path are at the same potential. There's no reason for anything to go. It's like holding 2 ends of a hose at the same height. Water's not going to flow anywhere. It just sits in the hose, okay? So as long as there's not a potential difference, nothing will flow. And if nothing flows down that branch, the circuit really hasn't changed at all. So it's going to behave exactly like before. Let me see if you can use similar thought processes to answer this question. It's not a terribly different question. I should tell you one thing. Although I feel like you should know this from lab at this point. This thing, ammeter, it's just a device that measures current. Okay, so they're labeling this thing called ammeter here in the middle. Just think of it as a device that sits in the middle of that wire that's just going to measure how much current passes through that wire. Okay? Now we'll write that up here. Any thoughts? I heard 0. Anybody else for 0? A couple of people. Anybody else have thoughts? 1. All current. So let's see. Once again, remember we need a path and we need a potential difference for current to flow. So that means there's already a path between A and B, but is there a potential difference between A and B such that some current would go that way? These resistors are all the same. So you could imagine, I don't know, starting around this way, you can see the current's going that way. It gets to this point and can split, right? So you can imagine some of the current's going to go one way, some's going to go the other way. But since the resistors are the same both directions, the same amount is going to go both ways. And they're both going to have the same voltage drop. So it's almost like the stream is here, then it splits, and then it goes down the exact same amount on both sides. So A and B are at the same potential. They're at the same level, which means there's no reason for anything to flow in between them. So the current splits, goes down, then goes down again, and then it's at 0 on the other side, okay? So you might write that something like this. You could say that this has a change in voltage of minus I times R, and this one is minus I times R, and then A and B are at the same V. So there's no delta V for current to flow. So the current there is going to be 0 through the ammeter. Okay, and then this one. Let me just say that this is the type of question that I can ask on an exam dealing with Kirchhoff's rules, because I really don't want you having to, I don't know, do a bunch of algebra. I want to see if you understand the problem. So in this particular case, they've already defined the 3 currents and some directions, and they don't tell you which loops they're going around. Of course, the obvious parts are like I could go around this loop, or this loop, or the whole outside. One of those equations applies to one of those loops and applies correctly. So it seems like it's like, oh, I'll never figure it out, but you'd be surprised how quickly you can get to the answer. one of the equations is correct for one of the loops in the circuit. I'll give you a couple of minutes to think it through. Medical research experience course. I don't want to do that. Maybe some of you do. It's not for me. I should probably look at this. I don't remember which one is the answer. When you think you have the answer, hold the correct number up in the air. Just so I know when you're done thinking. This would be incredibly mean. I wouldn't do this on the exam. That would just be wrong for a problem like this. So, no. Anybody find their way to that answer? Maybe a few people out there. Yeah. So starting anywhere up here, really, working our way around. This is a step up of 2. Then we're flowing with current I1. So that's 1 times I1, negative. And then a -4 as we go across that one. And then again, in the same direction as the current, -2I2 equals 0. So just a little bit of trial and error, I guess, is one way to sort of work through this. You'll notice 4 of them start with a +2, okay? Looking through, I've only got this one 2-volt option. So that's starting here and going across this direction, after which, well, I've got the option of doing what I did, or basically going around the outside. You should quickly try to trace around those and see number 1 falls apart, number 2 falls apart, and you can use a little trial and error to sort of get to the answer. Yes.
Would this mean the full 4-volt batteries charging?
The 4-volt battery charging. Maybe. I can't 100% say for sure in this particular configuration because we also have a lower voltage battery, which is the 2, and then the 6 is over there. I can't say for sure. Yeah, can't say for sure. Anyone else? Yeah. No.
I had a question about the last slide.
The last slide. Yes.
For this one, if doesn't matter if we have like 3 or 4 of them battery,
Does it matter if
have more batteries?
we had more batteries? If we had more batteries, the problem would get significantly more difficult. If we just had multiple ones in that bottom part of the loop, it'd be basically the same idea. But if we started putting batteries next to the resistors in there, yeah, I'm not going to go that far. Okay. Yeah.
Had the ammeter been put on the other 2 corners, then there would have been a full current.
On the other 2 corners of the square.
Yeah.
So here and here.
Yeah.
If that were the case, then current is flowing through this one and it's flowing through that one. So
Then it would just be full current.
the whole thing. Aye. Right. Let's see. We are actually not going to do this, and there's a couple of other things I want to cross out. Let me scroll forward. This is actually an extra slide, and we're not going to do this. And we're not going to do this. This is bonus material that you don't need. So there we go. Okay, you can kind of see what's left in the chapter. 2 things I want to talk about. First of all, a new type of circuit. And it turns out that you just basically have some set equations for these. If you can kind of understand the basic idea of how they work, you can quickly get to answers. So I'm going to describe how they work, describe the equations, and we'll do an example, and then we'll have the other thing about lab-related material. So notice, this is a new circuit called the RC circuit. It is exactly what you might expect. It's a circuit that has both a resistor and a capacitor. It's a combo circuit, a little bit of both. So it could be multiple resistors, it could be multiple capacitors, but it has at least one resistor and one capacitor in it. So you will notice here in this first circuit on the left, we've got a voltage source, we've got one resistor, we've got one capacitor, and currently there's a switch up there that's open, so nothing is happening. The circuit is just sitting there. We're going to say at the starting time t equals 0, we're going to close the switch. Okay, and you'll notice this just agrees with what they've said here. At earlier times, the switch is open, nothing is happening. Oh, that's not how you spell nothing. And then after t equals 0, the switch is closed, and you'll see that current is flowing toward the capacitor, and we would say here that the capacitor is charging. And over here at the beginning, the capacitor is uncharged. And you may remember we talked like in some detail about sort of how a capacitor charges, and we talked about like, yay, they have a place to go, and the charges start to run that direction. And as it begins to fill up, it's like, there's more like charges over there. I don't necessarily want to go. And it gets more and more difficult to fit more charges on because of the repulsion. And at some point, the capacitor's full, the current stops, and it's just done. And then I can disconnect it and go use it to power something else. What we're doing at this point is sort of zooming in on that period of time where charges are running over to the capacitor, filling it up. Previously, we just said it happens, now it's charged. We're now going to look at that charging process. That's what's happening here. So we go from a case of an uncharged capacitor to a case where time is going forward and we're beginning to fill up the capacitor. So based on the description we had before, maybe we start with lots of charges going. They're like, yay, so that's a lot of current. But then as time goes by, less and less charge goes that way. The current starts to drop until the capacitor's full, and then there's no current at all. So it's like I have a temporary circuit. Something happens for a little period of time, and then it's just sitting there waiting for me to disconnect the capacitor and go do something else, all right? So what's going to happen in these circuits is that the potential V, the resistance R, and the capacitance C are going to be constant values. They are fixed things in the circuit. The battery has a certain potential. The resistor and capacitor are physical things that have a value. But some other things are going to be changing. So we could say that the current in the circuit, the charge on the capacitor, and the voltage across the capacitor will be changing with time. As time goes by, we're going to have different values for all those. Previously, we just looked at Q and V sort of at the end. It's completely charged. What's the potential difference? How much charge does it hold? Now we're looking at all of the times in between when it's at different states of charging. It's partially charged. So we're going to have three things in the circuit that are constant and three things that are varying with time. They are functions of time. So we can no longer just say like how much charge is on the capacitor without asking when. At what time do I have a certain amount of charge on the capacitor? Okay, because it's always going to be a different amount. In this type of circuit, we just can't say what is the current. You have to say when do I, at this particular time, what is the current? Okay, because everything is going to be changing. This is what that looks like graphically. So here on the left, we have specifically the charge that's on the capacitor as a function of time. You can see that we start out with no charge, and then that charge rapidly builds, but then sort of begins to tail off as it gets closer and closer toward full, okay? So it starts out quickly and then begins to reach some maximum value where I have the maximum amount of charge on the circuit. So this dotted line represents Q equals C times V. This is the maximum charge on that capacitor. So over time, it's approaching that maximum. On the right-hand side, we have the current that's flowing through the circuit. And you can see we start at an absolute maximum value. As soon as I close the switch, it's like current, yay! But then very quickly, the amount of current that's in the circuit starts falling off and it's approaching zero. Eventually it's going to be basically arbitrarily close to zero if I give it enough time. So a couple of different things I have to tell you about this. First of all, what to start with? Let's write an equation for this one. So Q, as a function of time, the amount of charge that's on the capacitor, is equal to Q max, the maximum you could possibly put on there, times 1 minus e to the minus t over a constant tau, the Greek letter tau. Notice there's going to be some constant values in here. The maximum you can put on the capacitor Q is, as before, equal to C times V. This tau is a time constant that has a beautiful name. It is known as the RC time constant. And it is something that sort of tells you how quickly this particular capacitor can be filled up. And the equation is the name. This is one of those cases where it's just like beautifully put together. So tau is literally equal to RC. You gotta love that. So it's called the RC time constant, and RC is the equation for it. Now, if I just have one capacitor and one resistor, this is easy. If I have multiple capacitors or resistors in series or parallel, I have to find the equivalent resistance and the equivalent capacitance and put it into that equation. And then T is the only variable there. So I can use this equation, put the constants in there, and then say, okay, after 2 seconds, how much charge is on the capacitor after 3, after 6, after 100 seconds, okay? It's a function of time. So this is the equation that we use for charging. We can also write a similar graph and say that the voltage across the capacitor as a function of time is equal to the maximum voltage it can ever be times this exact same thing. And it turns out you're basically going to get a curve that looks almost exactly the same if you're talking about the voltage on the capacitor. The shape looks the same, the values are of course different. So these functions essentially graph for you an increasing exponential function. It's something that represents a graph like that starts off fast and then tails off towards some maximum value. The current, as we said, is that shape. It's a decreasing exponential. It starts at some value, rapidly falls off, and then begins to approach 0. We can write a function for this and say that the current through the circuit is equal to something that looks just slightly different, I max. And this time we leave off the 1 minus. So it's just e to the minus t over tau. So functions that look like this are increasing exponential, and a function that looks like this is a decreasing exponential. So if you can sort of remember the quantity and what it's doing while charging, which ones are getting bigger, which ones are dropping off and getting smaller, you can remember which equation you're supposed to use, the 1 minus version or just the one without the 1 minus. This describes putting charge onto the capacitor, okay? Now we can take that exact same capacitor and put it in a circuit of its own. Notice in this circuit, I have a capacitor and a resistor and a switch. There's no source of voltage. If the charge is going to move, all of that charge is coming from the capacitor until it runs out, until it has nothing left and it's back to just being 2 conductors that are near each other. So you'll notice we're going to do a similar sort of thing. They said at t less than 0, the switch is open, nothing is happening. And then at t equals 0, we're going to close the switch and charge is going to begin to flow. And you can see it leaves the positive side of the capacitor, goes around, it's trying to get to the other side to balance things out. But that current can't last forever. It's going to die. That sounds sad, okay? The capacitor is sort of like a short-lived source of voltage, a short-lived power supply. So in this particular case, we're going to start with the maximum amount of charge we're ever going to have on the capacitor, and we're going to run out. We're going to start with the maximum voltage, and we're going to run out. We're going to start with the maximum current, and we're going to run out. Question?
Like, where does it go? Like, if it just stays in that loop, does it get lost through like the resistance and like the heat wire or something? Like,
Where does it? What's
like
it?
the current itself.
The current. So if you imagine the current as just being positive charges, it's literally going to the other side of the capacitor just to balance out those negatives and make it neutral once again.
So but okay.
Yep, good. Okay, your question? Or it just got answered? Yeah?
No.
So do we just always assume max capacitance?
You might be given something for like what charge we start with here, because it could be partially charged, and then you're working from the maximum that it ever was when you made the connection. So it starts with whatever it has. It can never go higher than that unless I connect it back to the battery again.
Right, so then would that just inherently become the max?
Yes.
Okay.
Whatever it starts with is the maximum for this discharging phase. Okay? So if I were to draw some graphs, actually I'm just going to draw one and it's going to have all the graphs. So whether it's the potential on the capacitor or the charge or the current, it starts as high as it's ever going to, and then it goes to 0 as a function of time. Which means that all of these are going to have the exact same equation. So we could say that the voltage on the capacitor is equal to, I hesitate to use the exact same term, let's say the starting voltage times e to the minus t over tau And charge on the capacitor is going to be whatever you started with times e to the minus t over tau. And the current is going to be whatever you started with times e to the minus t over tau. So in this particular case, everything is a decreasing exponential because if you give it enough time, all the charge runs out and the current just dies. The circuit dies, all is dead, everything is lost. You have a question?
Yeah. So you said it becomes neutral because the capacitor becomes neutral, right? And then just the resistor works, that's why we lose the current?
I wouldn't say it's why we lose current. As current flows through it, it has collisions, it could do work on whatever's in there at the time, maybe generate a little bit of heat or something along those lines. But it's just the fact that the charges, like charges, repel each other and attract, or the same charge, excuse me, like charges repel each other, opposite charges attract, that they want to get back to the other side and neutralize everything. That's the reason the current stops flowing. I no longer have a repository of charge on one side that really wants to get to the other side. It's not because of the resistor, it's simply because the resistor just happens to be along the path to the other side where the charges want to be. Yeah. Oh, sorry, I'll come back.
So does the current just flow until the charge is evenly distributed throughout the wire?
Not evenly distributed throughout the wire, but you have equal positives and negatives on both sides of the capacitor. So if I zoom in on this, we start with a situation where, and how should we put this? Let's imagine that this is like more positives than negatives. Okay, there's still some negatives that's perhaps scattered in there, but it's more positive than negative. And this side is more negative than positive, even though there may be a few positives hanging out. Well, since I have too many positives here, positives are going to repel each other and start to run around and come to the other side and begin to fill this up. Once I have equal numbers of positives, negatives down that side, I'm also going to have equal numbers there. And now it's like, oh, we have no reason to go anywhere. There's no net repulsion, no net attraction. So it's not being spread through the wire. They're literally, they make a trip around and stop. And once that all balances out, everything's done. Does that answer or satisfy the
I
remainder
just
of your
want to know
question?
if the resistor has like an effect on it, like, or no? Or if we remove the resistor, will it still happen?
If you remove the resistor, the whole process is just going to happen faster. You could think of the resistor as something that sort of slows down the process, so it's not like the charge immediately balances out. Maybe I would like some current to occur for a period of time. The resistor just sort of spreads it out through time. Yeah.
So I don't know why, but looking at this, the only thing that comes to mind is the cell phone battery. So what we're essentially doing is pushing through current that would then run through a resistor until the point at which both of them are equally charged, and then when you plug it in, you would then force
Yeah.
it comes back. So you have this kind of like difference.
Yes. So capacitors are actually being looked at as replacements for things like batteries we recharge over and over and over again. At this point, we don't get as much out of them as we do with a traditional battery. The concept's the right idea though. Like we connect it to a power source, charge it up, and then it's temporary. At this point, having the extra chemistry and everything in there to keep the charges apart, that's something that can last longer. Capacitors are generally used in a circuit like this for something where you need a burst of charge just over a split second or at maximum maybe a few seconds. And that's as good as we get. But your concepts are kind of the same. If anybody remembers, it feels like we talked about these things before. Yeah, the disposable cameras, yes, we talked about those in here. That's a case where you need some charge briefly just to flash the bulb, right? The flash on there. That's essentially what this is. It's a charging and discharging circuit. You hold the little button down, it goes, whee, it makes a little noise. That's when we closed the switch and tried to put as much charge as we could on the capacitor. And then when you actually take the picture, it's closing the switch the other direction, taking a battery out of the loop and saying all the charge just runs out. It's quickly gone. Everything is lost. Nothing else is happening. Look into supercapacitors if you want to look into that more, and look at the research about using those as replacement for chargeable batteries. Okay, let's do an example with this. Let me show you how some of this comes together and works, and then we'll be just about done for this chapter, and I'm going to give you a problem to work, and we'll be done for the day. So let's see. Let's say we had a circuit that looks something like this. Let's switch colors. I'm going to put a resistor here. We'll call that R1. We're going to go over to here. We'll call that point A. What do we want to do here? Ignore some of these extra lines. My apologies. We're going to say this is a switch that can sort of go to two different points. So that might be a little different, but hopefully you can get the idea. This is R2. We've got a capacitor over here. And then we're going to have a resistor 3 there. And then our source of voltage. So that thing in the middle is a switch. It's just I can easily put it over to point A and do one thing, or I can put it over to point B and do another thing. It's a way of combining both charging and discharging circuits in one diagram. And on top of this, I'm going to give you some numbers. So the voltage is 50 volts. Resistor 1 is 10,200 ohms. Resistor 2 is 20,000. And resistor 3 is 1,300. The capacitance is 120 times 10 to the minus 6 farads, or 120 microfarads. And eventually you will have all that written down. Solve the problem.
Did you say 50 or 30 volts?
50. Follow the red dots. You're getting sleepy. Okay, so let me describe a couple of things about this circuit first of all. If I move this switch and make a connection over to point A, notice what I have. In that case, I'm connected to everything around the outer loop. But this resistor is not in play because there's no path, no closed path that goes through that resistor, okay? I will have a capacitor, 2 resistors, and a voltage source. So I'm going to be charging the capacitor. If instead I connect it over to B, well then this whole part with A and resistor 1 and the voltage source don't have a complete path. So they're essentially disconnected, not going to do anything. And then I just have this right loop where I have a capacitor and 2 resistors, okay? So A is considered charging, B is discharging, all right? So let's describe what we're going to do. We are going to start at time equals 0. We're going to move the switch to point A. This means we're going to be charging the capacitor. We'll say that it's initially uncharged. And we're going to leave it that way for a few seconds. Okay, so specifically, we're going to charge for 4.7 seconds. Maybe that's enough to completely fill the capacitor, maybe it's not. we are going to switch, for whatever reason I can't write the word switch, over to B. At which point we'll be discharging the capacitor from whatever state it reached during that first 4.7 seconds. And then we're going to discharge for 3 seconds. And at this point, I want to find a few things. I'd like to find the voltage across the capacitor and the charge on the capacitor at this point in time. We're going to charge for 4.7 seconds, discharge for 3, and then at that point, I'd like to see exactly how much voltage there is across the capacitor and how much charge remains across the capacitor. So first of all, let's solve for some time constants. I need the time constant when we're switched to A, and I need to find the time constant when we're switched to B. So this is just going to be R times C, and this one is going to be R times C, but I need to look specifically at what R's and C's are in the circuit at that point. So let's see, when I'm switched over to point A, we're just dealing with this outer loop. You'll notice that R1 and R2 are then in series with each other, so I can just add them. So that means when we're switched to A, this is going to be R1 plus R2 times the capacitance. So that's 10,200 plus 20,000 times the capacitance, which is 120 times 10 to the minus 6. Both big and small numbers. You should get, after all of that, a nice number like 3.6. And the time constant is time, it's measured in seconds. That's not too bad, right? What resistors are in play when I switch over to B? Make this connection. If I'm switched here, I just have this part. So R2 and R3 are in series with each other. Okay, so we can go over here and write this as R2 plus R3. And I still just have that one capacitor. So let's see, R2 is 20,000, R3 is 1,300, and the capacitance is just like what it was before. So that comes out to be 2.6 seconds. So we're going to use both of those values in our equations coming up. So I can't find anything out about how much voltage and charge I have left over at this point unless I find how much I charged it up to begin with, okay? We don't know if it reaches the maximum values or not, so we're just gonna have to find out. So let's start by finding the voltage across the capacitor at time equals 4.7 seconds. So for charging, we write this as Vmax times 1 minus e to the minus t over tau. And we're just going to plug all the numbers in and see what we get. What is the maximum voltage it can ever get in this circuit? We're connecting it to a battery that has a certain voltage. If I leave it there forever, what value is it going to get to? 50. It can't get any higher than the voltage I'm supplying to the circuit. So we can say that Vmax is going to be 50, and we'll multiply that by 1 minus e to the minus 4.7 over tau A, which is 3.6. You might want to try punching that in your calculator just to make sure that you can use the e function, the exponential function on your calculator. So you want to divide the negative 4.7 by the 3.6 and then hit the e to the x button to get that number. And if we all end up on the same page, you should get about 36.4 volts for VC at the end of our charging phase. Yeah.
That 3.6 under the 4.7 negative.
That is 3.6. Negative 4.7 divided by the 3.6 time constant we got up there. Okay.
That's the voltage across the capacitor.
That is the voltage across the capacitor at that point in time. The time change is making the light in here different. The light is getting low. Yeah.
Why do we have the V max 1 minus dV versus negative?
That's the equation we use during charging. For any quantity that's like increasing towards some maximum, that's going to be the function that we use. Okay? So the maximum value is 50. We didn't leave it there long enough to charge all the way. As far as it made it was to 36.4. So if I were to go back and look at our charging graphs, it's almost like, I don't know, we got to like about here and said, enough charging, let's start discharging it. Okay, we didn't allow it to go all the way up. So let's see, we could, if we wanted to at this point, we don't need to define what we want to find, but just a little bit extra. At this point, we could say that the charge on the capacitor is equal to C times V. And this would be the charge at this point, not at any point, it's just how much charge it currently has. And it's going to be 120 times 10 to the minus 6 times this 36.4. You would find 0.0044 coulombs on the capacitor after 4.7 seconds of charging. So we sort of know where we stand when we start discharging, okay? That's as far as we allowed it to charge. Are you okay with the charging part? It's mostly understanding the circuit and then just using these equations. Just plug the numbers in and see what you get, okay? So once we switch over to discharging for 3 seconds, this is going to be my starting voltage for that part, and it's going to start to run out. So we're going to say VC at t equals 3 seconds is V start times e to the minus t over tau. Except now our time constant is when we've switched over to B, and our starting voltage is this, and we're not using 1 minus because this is a quantity that's falling off, it's not a quantity that's growing, okay? So if you plug your numbers in here, you're going to have 36.4 times e to the minus 3 over 2.6, which should give you 11.5 volts remaining on the capacitor after 3 seconds of discharging. And then you can once again use Q equals C times V, so that's 120 times 10 to the minus 6 times 11.5 volts, and it'll tell you exactly how much charge remains, which is 0.0014 coulombs remaining. Yes, you can do this, maybe. Review it, think about it. I think you can do it. Anybody? Any questions up there? Anything that's bothering you at all? Okay. For the remainder of the time, yes, there's a little bit in these slides that I still want to talk about. I'm going to start class with that on Thursday, because we have 16 minutes remaining, and I would like you to try to work this problem using Kirchhoff's rules. So maybe try it yourself, maybe find a couple of other people around you and work it together, if that helps, and see what you come up with, and then after You have an answer, show it to me if you want to. And then leave and go vote. Okay? Please? Maybe.